Hello, welcome to our next video, lab report number 8, lasers. I'm Diego.
I'm Tyler.
And our lab TA is still at VARTS. So that's the line of the experiment. For part A, we got the laser cavity alignment. For part B, we got the fabric period spectrometer. Part C, optical spectrum analyzer. And part D, electrical spectrum analyzer. So in part A, we align the arrays with the green laser. We adjust the concave mirror after aperture. We align a Heaney gas tube with the green laser going into the tube. When the gas tube is on, a red laser should be visible. As showed the video, Tyler was tilting the mirror and stuff like that to make the laser going through it and to offset the high mode of the laser. So here's the video of the different mode of the laser. Laser intensity can vary depending on the mode. TM0 tends to be most uniform. As you change the mirror position, the new spot can emerge.
So for part B, we reflected the laser into the fabric period spectrometer with 2 mirrors. Then we measured the T mode and T FSR at 1.5 gigahertz. Then we solved for V mode, and then we compared this value, 4 gigahertz, with the one that we found using the formula C over 2NL. Here's a video of the setup. So for T mode, we found 0.700 milliseconds, and for T FSR, we found 1.59 milliseconds. This gives us a calculated V mode of 0.660 gigahertz compared to the estimation using the L of the cavity of 0.612 gigahertz. So for the conclusion, we found that spacing can be found both theoretically and experimentally with relatively low error, which can also be used to find wavelengths of unknown light sources with multiple different wavelengths.
So for part C, we send the Heaney laser and red LED into an optical spectrum analyzer. We measure the wavelengths and width of the primary mode, and we take note of any other mode separation. So here's the video of the procedure. So the laser goes into the mirror, got reflected back, and got reflected to the optical spectrum analyzer. So here's the second setup with the same thing, but a different optical spectrum analyzer. So here's the peak that we register into the second setup. We measure the length to be estimated to 0.22 meters.
For the cavity.
Yep. Oops. The laser is nearly one wavelength with no measured deviation, but however, the laser isn't exactly one single wavelength. There's some fluctuation due to error and manipulation.
Okay, so for part D, we measured the length of the laser cavity ahead of time as 0.22 meters. Then it was sent into the ESA with the below specifications. Here is pictures and videos of the setup, and the high peak on the right we found. So only one peak was observed at 694.4 megahertz. We calculated our 681.8 megahertz using C over 2L. And this follows up with some of the theories, since the L tends to be slightly smaller than measured, which would mean that the actual hertz should be slightly larger than measured, which would make our error very, very small. And the ESA follows part of the electrical signal that mimics an AC signal to find the frequency.